Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And here we're going to illustrate part 5 of a one-way fixed and X ANOVA little mini-series that I'm doing in R. And there we're looking at f-tests and confidence intervals for the treatment effects. Now, I'm assuming that you have already watched parts 1 through 4. So I'm going to highlight what we've done in parts 1 through 4 and run it so we can have those functions available. Now throughout this series we've looked at this example from Montgomery, the titled Design and Analysis of Experiments. It's the third edition, an example 3.1, and they called it the tensile strength experiment. So basically they have fabrics and they put different percentages of cotton in these fabrics, and then they try to tear them apart, and they look at the tension that it takes, or the force that it takes to tear these fabrics. That's called tensile strength. So they look at fabrics with 15% cotton, 20% cotton, 25, 30, and 35% cotton. And so I'm going to run parts 1 through 4, and then we'll arrow back down to part 5, which are the f-tests. Now, we've created an ANOVA model, and we've stored it in this variable OWFE, which stands for one-way fixed effects. And if we look at it, we get this summary here, which gives us, degrees of freedom, sum of squares, mean squared, a f value, and a p value. And in parts 3 and 4, we derived each of these values. And we're not going to do that here. We're just going to re-illustrate that the f-test is actually the mean squared for treatment divided by the mean squared residual, or mean squared error, and we get this f value of 1475.6, which is this value. Now the p-value is we take that p-value and look at the area in the tail based upon it, and we do that with this pf function, and notice that these p-values are the same as they should be. So that's how they calculate that from scratch. Now to look at confidence intervals for the group effects, so really we're looking at a confidence interval for mu plus tau 1, or confidence interval mu plus tau 2, etc. So it's the group effects. And here we printed the group means for each of these. So this is the 15% cotton blend, 20, 25, 30, and 35% cotton blend in the fabric. And so these are the average tensile strengths. Now the standard error associated with these effects is the square root of sigma squared over n. And n is the number of replicas. So an unbiased estimate for the error variance, sigma squared, is the mean squared error or mean squared residual divided by 5, which is the number of replicas. So I cheated and just put 5 in there. And so we get 1.2, or 269. Later it's going to round it. R will round that to 1.27 when I print it out, and I'll show you in a second. So now we create the plus minus part of the confidence interval. So notice this piece over here, the square root of the mean square divided by 5. That's the standard error associated with each group effect. And then the t value is this, the t sub alpha over 2. That's what this represents. Now I repped it 5 times because I'm going to do this in a vector. I'm going to take these group means that we've already printed out and just add this and subtract this, and that's going to create the confidence interval. And so that's what this next command does. It combines all those, and just we subtract the plus minus part, add the plus minus part, and we get this confidence interval. And so the confidence interval for the group treatment 1 effect is 7.15 to 12.44. That's the confidence interval for the average tensile strength for that group. Now, one note, R has a built-in function called confidence intervals, And we created this model, one-way fixed effects ANOVA, and we stored it in this variable. And so if we run that, it automatically creates confidence intervals for the parameters in our model. Okay. Now, here there's, the treatment effect. The parameters are, the treatment effect for 20%, 25, 35%. These are actually the differences between the base, it's the 20% cotton minus the 15% cotton. So this is not a direct comparison of this, because these really the difference between two means. But the intercept is actually only the effect for the treatment 1, the 15% rate. So if we look at this value, it equals the C15, right? 7.15, 12.44, right? As it should be. So this is what R produced, and this is what we did by hand. Now we have the confidence intervals for the other means too. Okay. Oh, and I'm printing this. I printed the ANOVA table, or because on the intercept, it's the it produces the standard error for that one effect. And notice it's 1.27, and that's what I was referencing earlier. So that's the value. Now this 1.796, that's actually the standard error associated with the difference between two treatment effects, and that's what we're getting to do now. Now I wanted to do this sort of automatically and just do it for every treatment effect instead of coding for every variable. And I'm going to show you my approach to this. Maybe there's better approaches, I don't know. There's a function called com_in. What it does is it treats all the combinations of these 5 two ways. So 1 and 2, 1 and 3, 1 and 4, 1 and 5, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5. So these are all possible two-way combinations. And you could actually stick a 3 there, and then it give you all three-way combinations. And also we do that for the treatment effects. So, and I do this so we can label it. Now we create the plus minus part. So this over here, the square root of 2 times the mean squared residual divided by 5, that's the standard error associated with that difference. And really the only difference between what we did before is this 2 is extra. Now here's the t statistic associated with it, so let's calculate that. We rep it 10 times because there's 10 treatment effects. So now let me arrow down a little bit. So here we take the group means, we take the combinations, the first row, and then we subtract the group means, and then we look at the combination of the second row, and then here's all 10 possible differences in the treatment effects. Now we're going to take that and just create one matrix of all these combinations. And so here's the unadjusted confidence interval for each of these differences. Now we're going to borrow this confidence interval again and look at it. So I'm going to have to raise this up. Now this right here, I'm going to highlight it down here. That is a confidence interval for the difference of C20 minus C15, which is this one. And notice that that's 100% the same as what we calculated up here. Now this one is C25 minus C15. So this one, it's actually 100% the same as this, right? As they should be. And the same way for 30, which is actually C30 minus 15. It's the same. And then for C35 minus C15, it's the same. Now, R does provide a pairwise comparison for all these. Now, this is unadjusted, so we're going to inflate the type 1 error by looking at all these. And R provides this function, Tukey honest significant difference, where it calculates all these pairwise differences and then adjusts it to maintain the family-wise error rate of 95%. And if you were to compare these to what we calculated here, ours are just a little bit narrower because it's not adjusted for multiple comparisons. comparisons. These are all just a little bit wider, but very, very similar. And then it gives you a p-value associated with each of these. And we may talk about this in a later video. Well, that's all I have for this video. The next video we'll look at part 7, which deals with contrast. So I hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.